What is dark matter? The first thing is that what is dark matter, that before I am explaining what is dark matter, why the dark matter is necessary, what is the role of dark matter, and how this matter came into the picture. It is too much important, so I am proceeding with some history, okay, that how this thing has came into the picture. 1933, Fritz Zwicky, a scientist, astrophysicist, an astronomer, who make his telescope to the Coma cluster. Now if you don't know the Coma cluster is kind of a very spherical thing, okay, which allows you to where there are so many, where bunch of galaxies are there. Some galaxies are dwarf, means tiny, some galaxies are too much big. They are called parent galaxy, and the dwarf is kind of a son or daughter galaxies. Okay, so it's a very it's a neighborhood galaxy in all this thing. When he tried to measure those velocity of dwarf galaxies, what he found out? What he found out that something is interesting going on, something is fishy going on. What happens is that, for an example, let me see. For an example, this is your, yeah, let me choose this thing. Let's point no pen. Suppose this is your what do we call solar system, and here is the sun. So what happens is that as you go away, the velocity of these planets becomes slower. Okay, because of this Newtonian thing, that velocity will decreases as if you go away from the sun. Okay, go from, because the the massive object in our solar system is your sun. Similarly, for galaxies, all the stars which is within the galaxy, if you go away from the center of the Milky Way or center of the galaxy, the velocity must decreases. As you can see here, it must decreases from the Newtonian dynamics. But what Zwicky observed that no, it doesn't happen this way. What happens is that the velocity of outermost stars or outermost galaxy remains constant. You see here, it remains constant. How is it possible? He proposed that maybe the mass then increases as you go out from the Milky Way or out from the center of the Coma cluster. How is it then possible? So what he did that, okay, let's measure that how much luminous matter is, luminosity of some galaxy or some Coma cluster is. When you take all the light from the telescope and you get some spectrum, and if you analyze those spectrum, you can calculate the mass of the Coma cluster or galaxy. What he calculated was, what he just observed, that something is really amazing, incredible, that yeah, the luminous mass, the mass of the Coma cluster or the galaxy isn't big, isn't too much to make this kind of position, that yeah, mass is increasing as you are going outward from the center. Something is going on really fishy. So what he said that yeah, there may be some masses which is kind of a dark, we don't getting any kind of light from there. People have told that yeah, I don't know, he may be mad or something else, we don't care about it. So what he did that, again people analyze all those things, and then they thought that yeah, maybe something is there. Okay, but it may happen that there may be some kind of something different is going on, maybe some statistical error is coming. What then people thought that we have something called gravitational lensing, something really interesting. Again, something really interesting. What is then gravitational lensing? A gravitational lensing, you can think of it, for an example, if you have this kind of lens, what does lens do? It bends light. So if you have convex lens, what will happen? So for an example, if you got this convex lens, what will happen? A light is coming from here and it will then converge to single point. Now maybe you got this diverging lens, light is coming there and it will simply diverge out. Okay, so lens simply distort the path of the light. But in space there is no any glasses are there, but these phenomena are actually happens, and this phenomena first addressed by Albert Einstein, because in Newtonian mechanics or Newtonian theory you cannot observe those distortion. This distortion because of the nature of space-time bending. So what does it mean actually, that space-time bending and so on? What you are talking about, space-time bending and so on? Are you crazy enough? Well, I am not crazy. You know, Albert Einstein's theory is itself a crazy to understand, but once you are just your head is getting big, nothing is crazy too much. So for example, there is a mass, and the property of mass that suppose this is a rubber sheet, and what happens, you put the mass, this will simply bend. So this won't be a straight line, but here it is something bending, again something bending. Okay, now this is the path of this space-time, and now this path is showing that space-time is bent. So the more mass will be there, the more bending is there, or more the space-time will curved. Now since light follows this space-time because it's kind of a path for it, whatever the structure of the path, light has to follow that path. Now for an example, you see here this galaxy, isn't it? If light is coming from it and there is nothing in the path, what happens? You will see the light easily directly in your telescope, no distortion. But what people have observed, that this is the galaxy and the image of the galaxy is right here, like this. They don't see this galaxy, they see galaxy like here. Oh my god, something really fishy going on. Now they know what has Albert Einstein taught, that Albert Einstein has said that because the light is coming from here and there is some galaxy, okay, and you know each and every galaxy there is a black hole in its center. We call it the big bull, or biggest black hole in the center. Okay, so we know how much light is emitting this galaxy, and we know the mass of the black hole here. So we calculate what is the complete mass is there, and now whatever the distortion is getting, whatever distorted image we are getting here, the amount of mass this will have, the amount of distortion we will see here. Okay, very good. So the amount of distortion we have observed cannot be produced what we have observed the mass with the help of its luminosity. Means that whatever the mass we have calculated so far with the help of the light it is emitting, it is not sufficient enough to produce this kind of distortion. The distortion has to be less, but it is too much. Why it is? Means that there are some extra mass in this galaxy which is unseen to us, which we cannot see in our telescope. And now the problem of Juicy, that he said that there may be some invisible mass. Now gravitational lensing is kind of a very concrete, it gives you the concrete evidence. Now here we see again, before concluding this, composite the image of matter inside the galaxy cluster. Suppose this is a galaxy cluster IE065756, also known as bullet cluster. The blue region shows the lensing map, while the pink region shows the X-ray data associated with the gas clouds. Because in every galaxy or coma cluster, there is some gases, hot gases, and it will emit some X-ray. If there is a matter, the usual matter, it will emit some X-rays. X-rays is shown by these red lines. Okay, and this lensing effect, how much lensing it will produce, this shown by this region. So the total mass will be completely this much. Wow, that is too much interesting. So if there was no dark matter, then we cannot see this kind of effect. There would be some kind of this much and this mass is enough, but we see extra thing, And this extra thing happens because of this dark matter, that there is something additional is there which produces extra distortion, and we call it gravitational lensing. So gravitational lensing has direct effect that yeah, there may be some dark masses, some dark stuff out there which we cannot calculate all these things, we cannot understand because it's not interacting. But how it is not interacting? You see here the pink region shows the gravitational lensing effect. This gravitational lensing is here only, it's not there, not inside. So if you have this Milky Way, so what is there? All the dark matter is actually surrounded outward, not its inside. Inside there is usual matter, outside there is too much dark matter. Oh my god. And thus this region shows that these dark matters are kind of something like they are not too much colliding with itself. So if maybe there was some collision, then this map that you are seeing, it may be some kind of little bit too randomized. It is not too much random, they are very swift and smooth. This smoothness says that yeah, these dark matter are really collisionless, okay, and they are really not too much interacting with this usual matter, because you see the distribution of those things. Oh my god. If you want to study dark matter, there is two ways to study. One way is that Einstein's gravity that we have to understand the geometry of all these things and so on, because geometry is manifestation of space-time curve. How this space-time is behaving is giving you the gravity or everything about gravity. And another way is particle physics, that we are asking that what kind of particle the dark matter has made up of. Is it made of some different kind? Or we may ask that yeah, maybe there is some particle which is from the standard model it has made up of, and maybe that's why it is interacting with very less interactively with usual matter. So there are basically two ways. One is particle way, what kind of candidate is possible, what is the velocity, does it make this kind of web-like structure and so on. And then another thing is that how this lensing effect is going on, what is the astrophysical aspect of this dark matter and so on. So there are two ways, and you cannot study alone one way, okay, you have to study it together. The whole team is working on this way, that yeah, we have to understand also particle and also the way Einstein has taught us to analyze the gravity. People are working on the sector of this modified gravity. They are saying that maybe we can twist the geometry and we can get rid of this dark matter, and we can say that it is nothing but the space-time curvature and so on. That's why we are getting this kind of stuff. So that's why this is too much, because nobody can say that there is no dark matter. And now it has been again concrete evidence that yeah, there must be dark matter, and we don't know what it is made up of. So we have to study in both way. So that thing now fixing that yeah, whatever the velocity of the stars, outermost stars or outermost galaxy in coma clusters, and what is the gravitational lensing effect, they both evidently says that yeah, there is dark matter. Now we understand what is this dark matter, how this dark matter, what is the link of this dark matter with the universe. And now that is very much interesting. Now as we are seeing here, for an example, this is the center, and I have told you that as you go outward the velocity remains constant. As you can see this curve, this flat curve says that the outermost stars or galaxy, they have this constant velocity after some threshold. Now this constant velocity, to achieve this constant velocity, dark matter must be there. If there is dark matter there, so because of this matter, it makes it makes the space-time in such a way that it has to be some static, and it gives the push that is required, but it is not interacting also. So it is making some kind of spherical web type or a spherical prism for this. I am not saying it's prism, but yeah, it's kind of very spherical prism you see here, and this is halo type, and we are saying it's kind of a very halo. We can also calculate what is the mass of this halo from from our Earth, or from for our Milky Way, because we know what is the mass of our Milky Way. Here is the sun, and here are some stuff like our stars and maybe nearby all the stars, and we try to understand the velocity of this thing. And from this velocity we can tell that what is the curve of these stars, and from there we can say that how much mass of this halo is there, and we can understand that what is the structure of this halo. And we got that this halo has spherical structure, it has distributed very smoothly and very simple. So that's why we are getting this flat tree thing, that whatever the outside, it remains consistent with this velocity. And from the glancing effect, we say that this dark matter, they have distributed smoothly and they are collisionless, means they are not interacting with the luminous matter, the matter we have made up of, and neither it is colliding with itself. So they are very much friendly, eco-friendly, you know. They don't care about anyone. Okay, but okay, it is a very interesting thing. So what we're gonna do here, we're gonna do something interesting. What interesting is that, let us again hang on, I think this is one. Okay, Windows Capture 2. So I think, okay, this one, hang on, dude, whatever you are, what I am going to say, yeah. So I am going to give you another thing about this dark matter, which is really too much interesting. And one of the person has worked, Dipanjan De, which has now completed his PhD from this IIT Kanpur, and I am giving you this very interesting idea about, more idea about this dark matter stuff, because it's really interesting. That's why. So yeah, let us start with his presentation. So that the thing is that the universe, what we have observed from the data from the telescope we have, by analyzing the matter, luminosity of it, we have analyzed the 73% our universe is made of dark energy. The energy we don't know, understand why this 73%, because the concept of dark matter is, dark energy has history again, because our universe is expanding. It is not that static, that whatever the thing is, that we see the stars, we don't see it like it is going away from us. But the Hubble has proved that, or observed that our universe is actually expanding. Means the room in which you are, it is actually making itself big. Okay, so what happens is, there's two chairs in the room, and the space between the two chairs is itself exceeding. What happens is, after some time, two people will go more distant. The more distance we will go, the faster you will proceed. This thing happens with our universe, that it is not just simply expanding, it is also accelerating. So the thing is that if something so much far away, it is going too much far away than us in a very accelerating way. Okay, so this given by v is equal to the velocity, you can calculate, is equal to Hubble constant times the distance, the co-moving distance. I don't understand too much about it. Okay, I cannot just simply explain with my wavy hand. We have to give you the equation for it. I am not going to give you. Simply saying that whatever in the room you are, it is simply expanding itself. And the 2 points are again expanding, and in some point it is not only expanding, it's accelerating itself. So 73% of the dark energy. Why dark energy? Because it has some kind of a fluid there which exhibit the negative pressure, and this negative pressure is not attracting the objects, it actually expanding. Repulsive force, there is a pressure, this negative pressure, this pressure has the thing like it is repulsive. For example, north pole, it is repulsive, south pole repulsive, negative charge, or positive charge, repulsive character, same thing. Now this energy is actually applying on this space time. It makes object, it doesn't make object to move further, it makes space time to just simply move away. That is the work of this dark energy. And 23% of dark matter. And the work of this dark matter is that it gives us a structure. For an example, there is no any dark matter, then you cannot imagine this kind of galaxies out there. This galaxy, the balancing galaxy, is because of this dark matter. And whatever the structure you are seeing, it's because of this dark matter. And now 4% is we are seeing as stars, galaxies, hot gas, which is made up of this regular matter in which we are made of. For an example, you see the periodic table, and there may be other particles we have not, elements we have not observed it yet, but yeah, there may be. But those matter actually emitting some light. So we are interacting those things, and we can see all those things. But the amount of those interacting, or we can say interactive matter, is too small. It's only 4%. And this 96% of the universe is made up of something which is completely alien, completely foreign. We don't understand what is this. And neither it is interacting with light. It gives you the effect of gravity. Yeah, it is bending space-time, it is expanding space-time. Whatever it is doing with space-time, or it is doing with some gravity. We don't know how this is actually interacting with other substances in our universe. Very well. So as we have already told you that whatever the thing that Juski has given, this rotation curve, it has coming from rotation curve, and we have also explaining what is the gravitational lensing. So the mass is actually creating this hallucination effect, a lensing effect. There may be some sources, light is bending, and we are seeing the images in distorted way. Now you see this distortion effect. For an example, there is some invisible mass, or maybe some heavy black holes. What happens is that it is distorting space-time so much that nearby stars has distorted. Now you see the ring-like behavior, and this distortion has some effect on this galaxy too. Now this thing has moved. Okay, you maybe have seen the interstellar. So this thing you can easily see there the effect of this distortion. It is moved there. So whatever the image, there is no any distortion here, but nearby you can see the ring like too much massive. Okay, and now you can see here again one image of this thing. Okay, so it's previous, this is something, now it is gaining some mass, and now this is like this, and again here. Now you see the distortion of this bone completely. This thing, it's invisible maybe, because black hole is invisible, but it is distorting this nearby galaxies and stars, and I see this distortion, amazing distortion. And again here, see here, all the distortions completely ring like. So there was nothing, the galaxy was galaxy, but the distortion is too much heavy. Again, if this mass is going on, so it is ripped apart. Now again this galaxy. So this kind of distortion has been observed by many scientists, many observations. Now you see this distortion effect. The more massive, the more distorted. So if there is more massive, then you can see this outer side. Okay, this outer side shows you that yeah, there is some kind of distortion. Now you can see this light. The stars is just little bit there, but the light is coming from here. Why? It is not that it is going through this galaxy. No, it is coming towards the path. That's what we see. Okay, and the light is coming towards us from here, so we see this kind of distortion. Okay, now you see here this distortion, like here again, this here distortion, this distortion, and from this distortion there is no any invisible mass, there is no any black hole. We suggested that there is dark matter. And you see what I meant to be the curved of space-time. The mass, the more curved the space-time will be. Here is the less, it will follow the geodesic, the minimum distance. Okay, again this will follow this geodesic. And from the Einstein's equation, the Einstein's field equation, you can easily calculate how much matter do you need. This is the part of matter to make some kind of a curved surface. And r mu nu minus half r g mu nu. R mu nu is called Riemann tensor. Okay, this is Riemann curvature. This is Riemann tensor r. This is Riemann scalar, and g mu nu. And this is a metric. For an example, you're writing dr square is equal to dx square plus dy square plus dz squared. So g mu nu is g11 is 1, g22 is 2 1, and g33 is 1. Okay, and g mu nu is component which is the coefficient of dx square, okay, dy square and dz square. T mean is the energy tensor, right? How much component of for an example, T00 will give you the energy density, and T11 will give you this pressure, how much pressure, and this rho or energy density is with the part of this matter part, and G. So this matter part is associated with this geometry part. So Einstein has managed to give you the amazing field equation which gives you one part is completely geometry, and this geometry has greatest relation with this matter part. And there is again this Poisson equation which says to del square B is equal to minus rho over epsilon naught. So curvature due to dark matter halo, as I have described you this halo. So halo is something, so halo is making you like this, you know, I have already told you that this halo, the mass is generally increasing. It was that for an example, here suppose this distortion, the effect of distortion will be here, it will completely less, so it is nearly flat. But here you can see the more distortion, so more will be speed. So as this dark halo will be there, so it will keep on distorting because the mass is heavy, so that it will maintain this velocity. The velocity must constant. Okay, so outside the sun there is no any distribution of matter, but space-time is curved due to this solar mass. For this type of system, source star is space-time, but for dark matter we can't use sun as space-time because its total mass is not concentrated at the center. So the thing is that as we are seeing this seeing our solar system, for an example, this is only the sun, so sun distortion effect across Pluto, obviously 9th planet, and for there, but you know, this dark halo is maintaining that the distortion must not just simply end, it has to be something like it gives you a constant velocity. And now there is too much mathematics is there that what kind of space-time, what kind of metric must dark matter follow, and he says that there is called Bertrand Bertrand Space-time. So he followed that there must be some kind of a space-time that dark matter can exhibit, and we call it that this is called Bertrand space-time. And he calculated everything that what can be the velocity, and this velocity that he matched with some astrophysical data, and it simply maintained with the help of this metric. You can see here this for time metric, and this is some beta, and beta is kind of a rational number which is in terms of pi, and it has to be rational number. Okay, so and alpha, this part goes for rotations, and this part for maintaining that what kind of potential it will give. It is a very nice concept, you know, and it shows that it is maintaining actually, and all these things. हाँ भैया 1 मिनट रुकिए. 1 second. Everybody needs food to survive, isn't it? So that is our survival thing. Food, people have given us the food. So yeah, this is the way he has calculated the density profile for this and the distortion with the help of this space-time. So if you know the metric, it is easy to calculate all these things. And he also calculated what kind of a T mean is there, what kind of energy momentum tensor is there. So it is a nice thing, and the conclusion was that BST satisfied all the dark matter properties, flat velocity curve, density profiles, lensing properties, etc. quite well, and so on. Can think of this space-time as a series of dark matter. So maybe things that yeah, dark matter, if there is a dark matter, obviously it gives you the space-time effect, because you see the curvature, the gravity has a space-time effect. Okay, so maybe there is a matter out there. So what kind of space-time possesses? It cannot possess this spherical concentrated at one point, but yeah, everything is distributed over everything. What happens in black hole? Black hole is that there is a one concentrated sphere, mass is there, one concentrated point, and all the masses is gone there. But in dark matter, the distribution is everywhere. So what kind of space-time could it be which actually giving you everything about that, the whatever the mass, I think whatever the space-time which can give you the idea that the mass is distributed everywhere. So Bertrand space-time enable you to calculate all this thing, Bertrand space-time, BST, and which this space-time actually proposed by Wollich, a German physicist, at 1992. You can download his paper. It's from IOP, and I can also provide you the link to actually you can understand all these things. So this is the way we analyze. There are too many alternative propositions there, and I don't think so that now I can describe you the particle part, that how people are actually understanding dark matter with the help of particle physics. This what I have described you, what is dark matter, how it came to the picture, why it is necessary, and if people try to understand it with the help of geometry, means Einstein's prospect, how one can actually analyze this from Einstein prospect. And one of the prospect, or one of the alternative, is that we can use BST. It's a research, not people won't actually tell you, it's kind of a ongoing research. Okay, so we use this kind of structure to actually understand dark matter with the help of Bertrand space-time. I will make you the video, okay, so don't worry if it is not clear right now. And I think tomorrow, or maybe day after tomorrow, we will talk in terms of particle, that what kind of candidate that dark matter may made up of. So it's very interesting thing to study dark matter. So if you got some interest in research and all these things, so jump on this thing, dark matter and dark energy. We'll talk about too many things like Lagrangian or mathematical things. It's very interesting stuff to study those things, or kind of things, and it's really interesting to talk on this stuff. So I think, yeah, it is not, one cannot say that it is a wastage of time. It's too much, there is too much to learn. There's too many things to unlearn, and also too many things to learn. You have to relearn so many things. While you are in research, we need to learn so many things in order to make everything really smooth and so on. So I don't know how many people have actually seen it, but I can say, yeah, it was amazing. Yeah, it was completely amazing. So thank you guys. If you haven't seen, no problem, but everything is everything. Thank you so much. We will meet you next time with an excellent explanation of particle prospect, that how we can study from this particle aspect of this dark matter. Thank you so much, and signing out.